Hello, algebraic reasoning. Today we're going to be playing with rational exponents and radicals. And so the objective today is to rewrite expressions involving radicals and rational exponents. 1. You can use rational exponents to represent radicals. In a radical expression, the number under the radical sign a is the radicand, the number n is the crook of the radical sign is the index. The index gives the degree of the root. For a cube root, the degree is 3. If there is no index, the degree is, and here's the first part where I get to talk like a human being, it is 2. Okay, so what it's saying is that when you see, for example, the square root of 81, there is actually a 2 here. Okay, and this means, like I said, square root. Recall what you know about square roots. Since 5 squared is 25, you know that the square root of 25 is 5 because they are inverses of each other. You also know that 25 to the 1/2 power is 5. Using the transitive property of equality, you conclude that the square root of 25 equals 5 to the 1/2. Similarly, the cube root of 8 is equal to 8 to the 1/3. Okay, so what am I really saying? I am basically saying this picture here. So the number in the corner, the number in the crook, I'm using air quotes here, is n is called the index. This symbol here is obviously called the radical sign, and the value inside the radical is called the radicand, or more broadly, the argument of the function. So again, the radicand, it can be called the argument to the function. Okay, and so what they're trying to say is that when we have something like a to the 1 raised to the 1 over n, this is the equivalent of saying the nth root of a. And a nice little way to remember this is just think of it as the person on the horse. And so at the end of the day, the person goes inside and the horsey goes outside. Okay? And they're illustrating it again here with a to the m over n. So again, the person goes inside and the horsey goes outside. Also note that you can rewrite this if you want, like so. And depending on the situation, one way may be more beneficial than the other. So it just depends on the situation. All right, so they're giving you a checklist of how to do this, and we'll talk more intimately about this shortly. But to simplify radicals, use a factor tree to put the numbers in terms of its prime factors. Group the same numbers of factors as this index that is shown on the outside. Merge these numbers onto 1 and place it on the outside. Multiply any numbers left on the outside together and the numbers on the inside together. So what this is saying, this is more or less so you have instructions written in case that's the way your brain works. But what we really want to do is we're doing the cube root of 343. The first thing you want to do is if you want to see if you can factor something out, okay? So you want to rewrite this as something times something. If you can rewrite it as something times something and it has it's a perfect whatever root, then that would be encourageable. But as is, I'm not sure what 343 is. So there's a couple of rules that you can use. One rule is that if the sum of the digits, so if I take 3 plus 4 plus 3, which is 10, if that is divisible by 3, then the number is divisible by 3, but that's not the case. So this number is not divisible by 3. This rule actually also applies for 9. It's not divisible by 9. It's not even, so it's not divisible by 2. It doesn't end in a 5 or 0, so it's not divisible by 5. 6, if it was divisible by 6, it would be divisible by 2 or 3, which it's not. So the next one is 7. So let's say I don't know if 343 is divisible by 7. I can do a long division to find out. This would be 4, 28, 12. We are subtracting. I don't know why I was adding. And so 14 minus 8 is 6. And look, we get 7 and 49. So this breaks down to the cube root of 343 becomes the cube root of 7 times 49. And I hope everyone realizes that 49 is 7 times 7. So 7 times 7 times 7. And so now the index is 3, which just means if you can group it in 3, it goes on the outside. And so this goes on the outside as 1 7 cubed root. Now, if there's nothing left, it's just 1, which means you really don't have to pay attention to it, and the answer is just 7. So when we let's look at the next one. So it's 256 to the fourth root of 256. So what am I going to do here? Well, let's say I don't know what this actually breaks down to in terms of fourth roots, but I do know that 256 is 16 times 16. I actually know this because of computers. So now we're going to take 16, we're going to break that down, and I know that that breaks down to 1, 2, 3, 4. 2 times 2 times 2, 4 times is going to give me 16, and then we can repeat. This is the fourth root. And so this says how many groups of 2's do we have? How many times can I group 2 into groups of 4? We can do this twice, so this becomes 2 times 2 on the outside, or simply 4. And there's our answer. So, to rehash, it says use a factor tree, which is just a way of listing the factors, to put it in terms of prime numbers. So here we see in here we wrote it as prime values, prime factors. Group the same numbers of factors as the index. This is just a fancy way of saying here we have a groups of 3 because this is a 3. And here we have 2 groups of 4 because the index is 4. Merge those numbers. Then look at rule 3. Merge those numbers into 1 and place it on the outside of the radical. So that's what we did here. These became 1 is 7. There's 2 groups of 2. 2 times 2 is 4. And that last step is exactly what I just said. Multiply the numbers on the left together and the numbers on the outside together. Sorry, on the inside together and the numbers on the outside together, which is what happened here. What happened right here. So 2 times 2, it becomes 4. Okay? Easy enough. All right, so example 2. Write each expression in radical form. So this is straightforward. Again, I said person on the horse, so 3 goes inside the house, 5 goes outside. Here, 2 goes inside the house, 3 goes on the outside. Person's on the person and the horse. So hopefully that makes sense. Sorry. Okay. More of this. Now we're going to do in reverse. So the number inside goes on top. Number outside goes on the bottom. And you go wide. So this becomes 32b cubed to the 1/5. I'm going to say that that's sufficient. The reason why I'm pausing is there's things that we can do here. But I'm going to say that that's sufficient. You could, for example, rewrite this as 32 to the 1/5, b to the 3/5 if you wanted to. And then 2 times 2, 5 times is 2. So this is 2b to the 3/5. But this is sufficient. Okay. So this is an important question. This is saying the cubed root of 27b. Okay. And this gets to the heart of how I want y'all to be thinking about this. What this index of 3 says is that you can remove it from the radicand, you can remove it from the argument of the function, insofar as you can you can have values in groups of 3. So we want to break this 27 down, and so you may ask yourself, well, what times what is 27? Well, 27 is 3 times 9, and we can break down 9 into 3 times 3. And so what we see now is that we have one group of 3 threes, and because the index is 3, this goes outside. And when it goes outside, it's just 1. And then we're left with the cubed root of b. And this, if you think about it, actually makes perfect sense, because what we're saying is that 27 is 3 cubed b, and the cubed root, from what we've discussed earlier, is the same thing as to the 1/3 power. So if you apply the power of power rules, we get 3 times 3 to the 1/3 b to the 1/3. And this leaves me with 3 to the 1 b to the 1/3, which is, again, the same thing as, well, why rewrite it? This. Oops. This, right? And that's why it works. So the idea here is whatever the index is, and for the most part, you're going to be playing with square roots because that's what you typically see in future classes. But regardless of what it is, all you have to do is break them down to their prime, and all a prime number is a number that's divisible in by itself in 1, and anything that's in groups of 3s goes on the outside. So here we have a bunch of problems for y'all to practice, and my recommendation for you is to pause the video now, write down these problems, and try them on your own. If you get stumped with one, watch my explanation and pause it and see if you can do the rest. But I felt it was important to go through a bunch of examples of this. The first one is going to be the square root of 125n. Now remember, anytime it's a square root, the index is 2. So we're looking at pairs of 2. Let me make sure I wrote that right. Yeah, square root of 125. Okay. So what's going to happen here? All right, so what's going to happen here, again, we just break them down. We break down 125. Now, I'm going to say that this is 5 times 25 because I know 5 quarters is $1.25, and 25 breaks down to 5 times 5. So what we'll see here is that we're left with one group of 2 5s. So that means I can put a 5 on the inside, but everything else stays on the inside. And that's it. Okay. So I guess I should call this number 1. And so number 2. Kind of putting these down in case I don't want to take up too much. I'm worried about taking up too much space. So square root 216v. Square root 216v. So again, you're going to break this down. You may not know what 216 breaks down to. If you're struggling with this, you may just say, hey, you know what? I know it's divisible by 2. And that's actually really easy to break down to 108. And how did I do that? Well, 200 divided by 2 is 100. 16 divided by 2 is 8. That's it. All right. And that works so well. Let me do that again with 108. I'll divide that by 2, so that'll give me 54. Okay. And we'll keep breaking this down. So this becomes 2 times 2. Now I know 54 is 9 times 6. I'll write that as 6 times 9. And then that breaks down v to 2 times 3, and then the 9 is 3 times 3. V. And just to be clear here, these two are these two, 2 times 3 is 6. 3 times 3 is 9. Okay? And obviously v is v. Okay, so the idea here is if I can put them in groups of 2, they can go outside and play. So these 2 can go outside and play, and these 2 can go outside and play. So I have 2 times 3 on the outside, and I'm left with 2 times 3v on the inside. So this is 6 and 6v. Okay? And that is it. One other point that I wanted to make here, and you can see it with both here and here, and I alluded to this earlier, is that if you can pull out a perfect square root, then you can just directly do that if you want to. But it's okay to systematically break it down as well, okay? Let's see if we can fit 3 here. 3 square root 512k squared. Square root 512k squared. So what's going to happen here? Well, again, if you're not certain of how 512 breaks down, you just, we know for sure it's even, so we can divide by 2, so it's 2 times, now what's 500 divided by 2? That's 250. What's 12 divided by 2? That's 6. So 256 k squared. Now, if you know, again, you see, you hear hesitation and pause in my voice, and that's because I know what 256 breaks down to. 256 is 16 times 16. And so because 16 is there, I can just directly, 16 times 16, I can directly yank out 16, and I'm left with 2k squared. Now, this is interesting because you're actually not done yet, and this is the new part. With k squared, this is actually saying 2 times k times k. Now I can pair, I have k paired, so I can actually take a k out. So these k's go on the outside, and I'm left with 16k square root 2 is my final answer. So the reason why I was trying to emphasize this fact here with the 5 and this with the 2, I guess I should be saying the 2 and then the 3, is that what works for numbers also works for letters. Okay. So the next one. Well, the next one is the same thing in terms of the number, right? So I'm actually going to just fit that in there. So number 4, where we ended up getting 16k here. So we know the number part is going to be 16. And we know we're going to have a 2 in here. Now we have m cubed, which is m, and m. So what we can see here is that one pair of m can go on the outside, and I'm still left with 1 on the inside. And there's a slick move you can do with this, actually, if you think about it. Because if you have m cubed, we're pulling out pairs. That's actually the same thing as saying dividing 3 by 2, right? Saying how many groups to do? Well, that's just division by 2. So you can just do 3 divided by 2, you get 2 with a remainder of 1. And what the remainder of 1 means is that you have 1 left over inside. So you have the 1 here, this is called the quotient, that tells you what the power of m is on the outside, and the 1 here tells you how many m's are left inside. Now, if we're taking the square root of something, m will always be 1. You can only have 1, because if you're pairing, right, if it's an odd number is just an even number plus 1. So there will always be just 1 left over. If there is anything left over, at most it will be 1. Now, be clear here. Let me be clear here. You can have nothing left over, right? And that's what happened with number 3, right? This is what occurred here with number 3, right? We didn't have a k left over inside. But at most, you can only have, at most, 1. Okay. Now, I am running out of space here, so let's see. I think, yeah. I gave myself another page. Okay, so let's do the next one. 216 k to the fourth. Now, I was going to do this on another page, but I already solved 216 for number 2. We got 216 to be 6 root 6. So this is 6 root 6. Now we have a k to the fourth. So if I apply the logic I just did here, 4 divided by 2 is 2. So this is going to give me 6. Oops. Again, I said 4 divided by 2 is 2. So this is 6k squared root 6. Okay. So 4 divided by 2 is 2, remainder 0. So there's no k in the inside. There's no k as the radicand, but we do have a k. We have 2 k's on the outside because 4 divided by 2 is 2. The quotient is 2. Now, on number 6, I'm wanting to do this on another page, but this is so easy. The square root of 100 is just 10, and then we're left with v cubed. Again, if you divide, 3 divided by 2 is 1, remainder 1. So this becomes 10v square root v. All right. Finally, number 7. Let's do number 7 on another page. So 7, what is it, 80p cubed? So what we're going to do here is we're going to break it down. Now, I'm going to follow my logic earlier and say we could take out, I know I could take out a 4, that's 4 times 20p cubed. And that means I could do another 4, because 4 times 5 is 20p cubed. And so we can take a 4 out, right, because there's a 4 here. And that'll leave me, or rather I should say we have 2 4s, 5p cubed. And then with the p cubed, again, 3 divided by 2 is 1, remainder 1. So that means we have 1p on the outside and 1p left inside. Okay. All right, next one. Number 8, 45p squared. 45p squared, square root. Okay. So again, if I can take a perfect one, in this case 9, go ahead and do that. So 9 times 5, p squared. Square root of 9 is 3. Put that on the outside. Or you could break 9 into 3 and 3, and so you have 2 groups of 3, so you have 1, 3 on the outside. That makes better sense to you. 5p squared. And then with p squared, well, 2 divided by 2 is 1, so that just means the p goes on the outside. Okay. All right. Let's see the next one. Number, what are we on? Number 9, 147m cubed n cubed. 147m cubed n cubed. And this was, what did I say, number 9? All right, so 147 is a little tricky. There is a rule, this always works, that the sum, if the sum of the digits is divisible by 3, so notice 1 plus 4 is 5, 5 plus 7 is 12. This is divisible by 3, then so is the number. So what that means is that 147 is divisible by 3, though now that I'm looking at it, I don't know why I didn't think about this earlier, I'm just going to take out 7. This is square root. So this is going to become 7 times 21 m cubed n cubed. So why did I choose 7? Because 7 very easily goes into 14 and 7, and so if the number is 147 or 147, it's really easy to do that. And then 21 is just 7 times 3. So now you have 7 times 7 times 3, m cubed n cubed. We have one group of 7, so that goes on the outside. Both the 3m cubed n cubed. And so now we're going to play with the variables. So that means we're going to have 1m and 1n on the outside. This is going to be square root 3 with an m and the n on the outside. I hope that you can see why, which is just that you divide by 3, divided by 2 rather. 3 divided by 2 is 1, remainder 1, and the same thing with n. So there you have it. And next we have number 10, 200m to the 4th n squared. You know, that's so easy. Well, let me just do it on the other page. 200 I'm saying 200, I'm writing 300. M to the fourth, N. Okay. The reason why I was like, this isn't bad at all, is because we know square root of 100 is 10, so this is 100 times 2 times M to the fourth N. So this is going to become 10 square root 2 M to the fourth N. If that's not clear, 100 is 10 times 10, so you have 2 pairs of 10 that go on the outside. And then now N stays by itself, but you have 2 pairs of 4, so this becomes 10 M squared 2M. So again, M to the fourth is M times M times M. You have 2 here and 2 here, so hence that's a 2. There you have it. Okay? I think I gave myself a lot. Oh. I allowed myself a page for each problem. So let's see here. 11 would just be, and I'll just fit it up here. And now we're going to kind of go into the fast round. Square root 75 is just 3/4, so we're going to be 5 root 3 x squared y. And then obviously x squared, there's one pair, so this is just 5x 3y. Want to stress again, 75 is 25 times 3, square root of 25 is 5, hence it goes on the outside. Okay, 12, square root of 64 is 8. We've seen this already, it's mn, square root mn. Number 13, square root of 16 is 4, u to the fourth, square root of that is u squared, 4 divided by 2 is 2. And then with the v, 3 divided by 2 is 1, remainder 1. So v, and then we have 1v inside. 28 is 4 times 7, x cubed, y cubed. And so this leaves me with 2 square root 7, x cubed, y cubed, which then we've seen several times again. 3 divided by 2 is 1, remainder 1, so you have xy on the outside with a 7xy on the inside. And there you have it. And those are your answers, okay? Want to stress, again, that when you're doing this, what you will see is that I'm always looking for a perfect square root to factor out. And so hopefully that's not too bad. Okay. Okay, a couple more examples. I'm going to try to squeeze these in. I don't have too much time. 252. So you have square root of 252. This breaks down to 2 times 200 divided by 2 is 100. 52 is 27. So this is 127. 127 looks like maybe it's not 2. It's not 3. Now that I think about it, 127 is actually prime. So this actually doesn't go any further than what we have here. That's it. So it's interesting. It doesn't always break down. Did I make a mistake? I did make a mistake. This is 126. Ah, makes more sense now. Okay, let's keep going. So I'm going to take out a 6. And then we can break down 6 into 2 times 3. And we can break down 21 into 3 times 7. Again, things that are paired go out and play. So 2 times 3 goes outside. 7's inside. 6 root 7 is the answer. Okay? And I'm going to have to stop here. I had delusions of grandeur. There's no way I'm going to finish this off in one video. So next video, I will be finishing this off. All right. Hope to see you all there.